Good afternoon, everybody. So today we are going to discuss one more example uh, for 2D motion, or a lot of times we call them projectile motion because when we throw something, it's going in this parabolic trajectory. So it's parabolic 2D motion. We will do one more example of that, and then we will discuss relative motion. And we'll touch on the circular motion briefly, but mostly we'll finish the discussion for circular motion in the next class. Okay, so let's take a look at this example. I'll give you guys a couple minutes to read this, and it's already have a picture drawing for you. So as you read it, you can try to, on your notes, try to add the quantities, label the quantities, and think about how do you gonna set this problem up. Okay, so give you a minute or two to read it. Excuse me. Okay, now let's look at it. Look at this problem together. We have this kicker that is kicking the ball at 30 meters per second. So let's label the quantities. V naught is 30 meters per second, and the angle 30 degrees with respect to the ground. So this is the angle theta is 30 degrees. Okay, so you can see it has both an x direction and a y direction in terms of motion. And we decided to put origin x and y like that. So let's put our origin here. So gonna put y here and x here. Okay. What else do we know? We also know that it's cross off the other side of the field at 3 meters, so over here. Okay. This height is 3 meters, and we're wondering how far away it is. So how far away is asking for the x direction. So we want to know what is this x in terms of the distance. So if this is x initial, then this is x final. And we want to know what is this x final in the horizontal direction. Okay, so I have labeled the quantities. Draw a picture, we did that. Let's label the quantities. We have done that. For 2D motions, right, we need to break it down into 2 different directions. So in terms of the physics, it's 2D motion. We need to look at x and y separately, right? Okay, so let's break down the V naught into x and y. So you can see that V naught is this blue vector here. This is V naught x. This is V naught y. Okay, so V naught x is V naught times cosine theta or sine theta? What is V naught X?
V naught X,
Yeah,
Cosine?
cosine.
thank you, Eric and Carlo. It's going to be cosine 30 degrees. And we have V naught that is given cosine, we know, and that is going to be roughly 26 meters per second. Now V naught Y would be V naught of sine theta, sine 30, and that's 1/2, so that's 15 meters per second. Okay, so I just say 26. Okay, so we have Vx and Vy. Going back to our physics, the motion in X, you still remember the type of motion in the X direction. What is it? What is the type of motion?
Horizontal.
Yes, in the horizontal direction. It's a constant velocity or constant acceleration. It's a constant velocity. Thank you, Tanis. So it's a constant velocity. And y is constant acceleration. Okay. And what is the acceleration? Do we know acceleration in y?
Negative 9.81 because it is the acceleration due to gravity.
Yes, that's free fall, so negative 9.1 meters per second squared. Excellent. So we know these, let's look at them separately. So the question is asking what is how far you're kicking the ball. So X is asking X final. So for constant X velocity, the distance you traveled is simply going to be velocity in X direction times time. Okay, so that's the kinematics equation we know for constant velocity. Initial 0. So we wanted to find this quantity, how far it is. So this is calculating how far. Okay, so we know V naught X, right? Now we just need to solve for T. And can plug it back into this equation. Okay, so we don't know time, but we are still giving information in the Y direction that we have not used yet. Okay. So let's solve for Y. So this is X direction, Y direction. Okay. Y is constant acceleration. So I'm gonna do Y final equals Y initial plus V naught Y T minus 1/2 GT squared. Okay. Initially, you're at the ground, so in our coordinates, that's 0. Finally, you're at 3 meters, okay, above. So that's 3 meters. V naught Y we know is 15. Time we don't know. That is what we need to solve for, right? So from this equation, we can solve for T. And it turned out there are 2 times. It could be, the answer is plus minus 12.9 over 9.8 seconds. So we'll get T equals 2.
Professor, we can't see what you're doing.
Oh, I'm sorry. And let me update my share one more time. Thank you for letting me know. Okay, there are 2 different times. One is 2.8. The other is 0.2 seconds. Okay, so we got 2 times, 2 solutions from our math. Which time do you want to use? This one or this one?
2.8.
2.8. How come it's not the 0.2 seconds?
It's the other side of the parabola.
So the 2.2 seconds is describing where? Is it even physically, does it even have a meaning? Sometimes on your math give you an equation, give you 2 solutions. One has physical meanings, one doesn't, which is okay. You'll take the one with physical meaning. In this case, we know 2.8 is the time it takes to go here. And does 0.2 seconds does it have any meaning, or is it not meaningful at all? So that is corresponding to the height at 3. So the ball reached the height 3, how many times? Once here, right? Yes, it has me, yeah, twice. Glenn, thank you. Also once here. So the 0.2 seconds actually is over on the left-hand side, but we want the right-hand side. Very good. So we're going to take the 2.8 seconds and plug it in. So you got 26 times 4.8 seconds, and you got how many meters? I have this here, 73 meters. It turned out to be 79.6 yard. Just wanted to let you know, is historically it is much less than this. The longest field goal is much less than this. So sometimes when you get an answer, you also wanted to evaluate the how reasonable your answer is. Now in this case, it's not really reasonable or not reasonable. Or if it's asking you in this question, like, is it likely a achievable goal? Or if you're asking you, like, you're trying to look at the strategy to see if this is likely going to happen. And then your answer might be, oh, given the longest field goal in history is 60 some yards, much less than this, we would think this is not likely going to happen. So some ways to evaluate your answer. Now, in this case, you can just say 64. Thank you, Carlo. That's pretty much your answer. You can stop right there. Okay, Eric, you want me to scroll back up here again? And this is how we solved the problem. Okay, I'll make it a little bit smaller so you can see the full picture. Yeah, thanks for the comment, Clement, because air resistance also plays an important role in real life. Here, we ignored air resistance. We didn't take that into account. Okay, so that's our example I want to do for 2D motion. Okay, further to demonstrate how we treat y and x separately. Okay, now let's talk about relative motion today. Relative. What do we mean by relative motion? So when we're talking about how fast we're moving, it's really implicitly we have a frame of reference. Sort of, I touched upon that in the previous class. Relative to what? Relative to who that you're talking about? You must have the experience that when you are driving a car, right? If there's a incoming car, or if you're sitting in a train, if there's another vehicle coming towards you, and you pass each other, and the moment you pass each other, it feels that they're going really fast because you're going one way and they're going another way. So relative to you, they're going even faster than whatever speed they're driving. So if you're going 50 miles per hour and they're driving against that direction 50 miles per hour, both relative to the ground, then their relative velocity to you is 100 miles per hour. So it feels like they're shooting by. It's really fast. So again, if you are again, we have the experience of using the belt in the airport, right? You have the walking belt. You can stand on it, and the belt will slowly move you from one side to another. Or if you get impatient, you can walk relative to the belt and you add some velocity yourself. So relative to the ground, now you have the belt's velocity and you have your own velocity to the belt, and your relative velocity to the ground is now much higher. You're going much faster. So this is what relative motion is. You can see it is very relevant to us. So for example, the one formula we need to use for solving all relative motion problems is this one. I'll explain what it means using this example. So let's say you have a train. Okay, the train is traveling with 30 meters per second. But again, relative to what? Relative to the ground. Okay, or in another case, we say relative to the earth. So V train relative to the earth is 30. And the person is walking relative to the train with 1 meters per second. Okay, you're walking on the train. So together, your velocity relative to the earth or the ground is going to be 30 plus 1, that is 31. So v, the velocity a relative to c, can be calculated by looking at the vector addition of a relative b plus b relative to c. So in the case of the train, it will be velocity u, or in this case, this person's name Mike, u relative to Earth is u relative to the train plus train relative to Earth. Okay, u relative to the train is 1 meter per second. Train to Earth is 30. So your velocity relative to the Earth is 31. So this is basically what the equation is trying to tell you. And you can see, you can break it down in how many little segments you want. So A relative to C, you have one more object in between. You can do A relative to B plus B relative to C to D plus D relative to C. So you can introduce another object if you wish. And as long as the beginning of this and the end of this is the beginning of this and the end of this, this equation holds. Later on, we will do an example with more than just 2 objects, with 3 objects. Okay. So this is something you have already done, the checkpoint questions, and I will just go through them relatively fast. You have a person standing on a moving sidewalk, and this is at the airport, that this belt moving relative to the ground is 2 meters per second to the right-hand side. And the dog runs toward the girl in the opposite direction. And the dog's velocity relative to the belt is 8 meters per second. What is the speed of the dog relative to the ground? Okay, so let's use the equation we have just developed to solve this. So the velocity dog relative to ground, okay, this is what is asking, dog to ground, is going to be what is given, dog relative to what? To the belt that is given, right, to the belt, plus, so what is the second velocity? I should add dog to belt plus what to what? Yeah. What do you think?
Negative belt to ground.
Plus belt to ground. Not negative, just dog to belt, belt to ground. So belt is sort of an intermediate step here. Very good. Belt to ground. Okay. Now dog to belt is 8 to the left. So you can say 8 to the left. I'm gonna say left to be negative direction then. Okay. And belt to ground is 2, but it's in the positive direction. So I'm gonna do 6. I get -6 meters per second in the x hat direction. Okay, so dog relative to the ground is moving 6 meters per second to the left-hand side. Now, if you're curious about the speed, then the velocity, the direction doesn't matter. It's just 6. Okay. So now the second question is, what is the speed of the dog relative to the girl? At first, you might wonder, well, I don't really, they didn't give me information about the girl. But then looking a little bit carefully, the girl stands on the belt. So the girl is relative at rest, relative to the belt. The girl and the belt, you can view it as one object in this case. They're moving together, right? Velocity girl to the belt is actually 0. Okay. So this question is really asking, what is the speed of the dog relative to the girl? You can replace that with what relative to the belt, because the girl and the belt are standing is together. They're moving at the same velocity. So dog relative to the belt is already given, is 8, right? So the answer would be 8. If you wish, you could add the girl in the equation by saying v dog relative to the girl which will be dog relative to the belt plus belt relative to the girl. Now, dog to belt is 8. Belt to girl is 0. They're moving together, so you still get the 8. So either way, you can get the 8 meters per second answer. Okay, so any questions on the checkpoint before we move on to the next question? Any questions on how to use V A relative to C equals V relative to B plus B to C? Is that clear? The only thing with the addition that you need to be careful about is the direction. Just be careful with in which way these velocities are pointing at. Okay, now let's look at another question. This is from your pre-lecture. This diagram shows at t equals 0 time, you have a snapshot of a green ball and a red ball. At this t equals 0 at this instant, are separated by a distance of 12 meters. Now the green moves with a constant velocity 6 meters per second to the east. The red moves with 2 meters per second to the west. So we want to translate that into a graph, and is asking you to use the origin to be the position of the red and the positive direction to be the east. Describe the motion of the green in the reference frame of the red. Okay, so don't be thrown off by the mention of reference frames. It's really just, you know, is really just asking relative to the red how the green is moving. So I had a little diagram drawn here. Let's go over it together. I take the origin to be the position of the red. So this is the red, and that's the origin, okay? And take the positive direction to be the right-hand side to the east. So you draw your axis this way. So at t equals 0, the green is located at 12 meters on the left-hand side of the red. So this is the green, which means the initial position of the green is negative 12, right? Because the red is at 0, the green is to the left, so negative 12. So by that information alone, you can get rid of some wrong answers. At t equals 0, x should be, the position of the green is negative 12. So this is negative, right? This is negative. This one's positive, this one's positive. Therefore, you know that they're wrong already. So now we have to choose between A and D, okay? Now, the difference between A and D is one of them has a positive slope and one of them have a negative slope. So what does the slope represent on the xt graph? On the position time graph, the slope represent what physics quantity? What do you think? Tennis, a velocity, thank you, and thank you, Cindy. Yes, represent a velocity. So now it's really a question of relative to the red ball, because it's in the reference frame of the red ball. Do you think the green ball is moving to the left or to the right? So imagine in your eyes, in the reference frame of the red ball is basically saying in the eyes of the red ball. Let's say you're sitting on the red. In your eyes, the green coming towards you to the right, or is it moving away from you to the left? It is to the right, Jasmine, thank you. Yes, it is coming to the right. The right-hand side is the positive direction. So in the eyes of the red, the green is moving with a positive velocity. So you should have a positive slope. And therefore D is the correct answer. And again, my screen is not updating. Let me update it, try to update it. So this one has a positive slope, therefore it's D. You can calculate how much it is, but you don't need that to answer the question. So the green relative to red is green relative to Earth plus Earth relative to red. Green relative to Earth is given is 6, and it's moving to the positive direction, so it's positive 6. Earth relative to red, now this one might throw you off. Earth relative to red is how much? How do we figure out this quantity? We are giving red relative to Earth though. We're giving that the red ball is moving relative to the Earth with 2 meters per second west. So Earth relative to red is how much? Is 2 to the east, yes, 2 to the east. So that's positive again, so it's positive. So it goes on, add up to be 8 meters per second, positive. So if you want to know what the slope is, that's going to be 8 meters per second. Okay, now let's look at this clicker question. A man is walking along the dotted line on a moving sidewalk, walking toward this fire hydrant. It's moving 1 meters per second. It's relative to the moving belt, and perpendicular to the belt, 1 meters per second. And the sidewalk is moving this way, 2 meters per second relative to the ground. And the sidewalk has a width of 4 meters. So it's asking, how far away will he be away? So once he go to the other side, he probably will be here, right? How far would he be away from the fire hydrant? So take a screenshot of this before you discuss the question in the breakout rooms. People have already come back. Please put in your vote to this question. Another 10 seconds. Okay, any last minute vote? All right, I'm gonna go ahead and close the poll and then we can take a look. So here is our results. Would anybody like to share with us that how do we begin solving the problem? What is the method that you used or someone else used? I see a chat from John said it takes 4 seconds to cross. Do we agree with that? How do we get 4 seconds to cross the side?
Yes.
Yes, we agree. Yes. Okay. Yes, very good. So a common strategy when we're dealing relative motion, sometimes we can. The trick is to treat these two different motions separately, independent of each other. Because we are given the person is moving relative to the belt, and also where is he crossing? It's crossing the belt. So we simply just can't. We don't even think about the ground. Leave ground away from the picture. So the person. The time it takes for the person to cross the belt would be the distance of the belt, the width of the belt to the velocity that is a person relative to the belt because he's moving along the belt. So that is going to be 4 meters over 1 meter per second, and that's 4 seconds. Yes, so that's 4 seconds. So this motion is independent of the moving of the belt, of the sidewalk, right? In those 4 seconds, how far did the sidewalk move? Then that is a motion relative to the ground, is constant velocity. 4 times, so this distance this way would be velocity of the sidewalk times time, which is 2 times 4 is 8 meters. Okay, so the person will be carried by the belt along this direction for 8 meters. So it will be away from the fire hydrant for 8 meters. The answer is D. You could, I'm just saying is that it's not the easiest way, but you could calculate the person's relative velocity to the ground. And relative to the ground, the person is probably moving in the diagonal direction because not only is going across, it's also moving down. So diagonally. Then you also need to find out the diagonally how long the person has to walk. And then you can find out the 8 meters as well. But this method that you guys used is more straightforward. Let's look at another quicker question. This one will pave the way for us to be able to answer the question in your pre-lecture. So we have 3 swimmers. They swim equally fast relative to the water. They have a race to see who can swim across a river in the least amount of time. Relative to what water Beth swims perpendicular to the flow and swims upstream at 30-degree angle. and Charlie swim 30 degrees downstream relative to the water. So this is all relative to the water. The water flows downstream. So this is the water to the right. Okay, so who gets across the river first? Okay. So I'll give you a hint. This is like the moving belt. In this case, the water is like the sidewalk. You're getting across the sidewalk. So who gets across first comes down to who can get across with the shortest distance. Okay. All right. So I'll let you again discuss this for about a minute or two. Okay, as you guys come back, please put in your vote. Yes, I see the message that your Wi-Fi got disconnected. No problem. You can sign back in. It's always enable people to join. Also, I want to make a comment. Some people are not active in the breakout rooms. So I wanted to please make sure if you do come to attend the class, make sure you stay unless you have emergency, so that you know other people could also you can benefit the most from coming to the class. You're not really your participation is not counted towards your grade anyway, so it's not like you're missing out on things if you're not here on the credit. But I do believe that if you do join, I hope everybody could participate in the breakout room discussion. Now, I believe you are able to ask a question or raise your hand in the breakout room. So in the next time, if you are assigned to a breakout room, nobody's active, simply just send me a message in the chat and I'll switch you. Okay, thank you for letting me know. Okay, any last minute vote? Okay, then I'm going to go ahead and close the poll and then we can take a look. I wanted to apologize. I misspoke. I saying the shortest distance that might be confusing. It's not the shortest distance. They all have to cross the river, which means they all have to cross with the same amount of distance because the river has only so much width, right? So it's like the width of the sidewalk that is decided. So whoever get across first has to do with the velocity, with the biggest velocity, get to cross the river with the shortest amount of time. So you can see this is our results. Okay, so now let's discuss how do we get the answer. So time it takes to cross the river is going to be the distance over velocity. So the distance would be the width of the river. So that's the same for all three. Now the velocity would be swimmer relative to water, which is in the direction of across. So you only if your velocity in this way that gets you across the water is perpendicular. I'm going to add little sign says perpendicular. Now this, if you're swimming this direction or this direction, is not going to get you across the water. So we want to know the effective velocity, which one is crossing the river. So by looking at these three different velocities, you can see we only want to consider the velocity in the y direction because that is enabling them to get across. Best has all the velocity in the y direction. So the y direction is all v0. Okay, and the y velocity is only a component of that. So it's in this direction. And you can see Anne seems to be doing two things, across the river, but also swim upstream. Now, C is Carly. Carly is crossing the river, but also swim downstream. Those two velocities doesn't matter. It doesn't get you across the river. So velocity in the y component for Anne is v0 cosine 30. For Carly is v0 cosine 30. So Anne and Carly will cross the river at the same amount of time, but they both be behind Beth. Beth has the biggest velocity and Beth cross first because cosine of 30 degrees is less than 1. Okay, so these two velocities are all smaller than v0, less than v0, less than v0. So yes, so the correct answer would be Beth. Who gets crossed first is the one who has the largest velocity in the y direction. Okay, now we have another follow-up question. So you realize that the previous question, we only care about the velocity relative to the water, but in terms of relative to the ground, you have your velocity relative to the water and the water relative to the ground. Both things have to add up to give you your velocity relative to the ground. So assume, again, you can swim relative to the water with this speed. I mean, half the speed of how fast the water is moving relative to the earth. So at what angle relative to the horizontal direction that you need to swim in order for you to go straight across the river. In order to go straight across, meaning that your velocity is perpendicular to the riverbed, okay? So 30, 45, 60, or no such angle exists. So I give you guys again a couple minutes to discuss this question. Okay, let's vote. Let's vote for another 10 seconds for everybody to finish the voting. Okay, let's, I'm gonna go ahead and close the poll. Here is our results. Seems to be we pretty much distribute across all kind of answers. So let me hear from our volunteer. Anybody would like to share some thoughts? How does your group discuss and what do you think? And how do we go about answering this question?
I used the water flow as a y component,
Okay,
and then I set it equal to 0.5 times sine of theta, because that's the y component of the velocity. The 0.5 is in reference to the magnitude of the velocity. So
okay, so this is 9.5, and this is the u relative to water. Y is 9.5 times 9 of theta. Is that right?
yeah,
Okay, so what do we set that to?
I set that equal to 1 because if you want to go straight across the river, then both of the velocities, the water's or the water's speed should be equal to your speed.
Okay. That's a very good point. You're on the right track. But I would argue just one thing to be different from what you said is instead of setting the sine theta to be the one water flow, I would set the cosine to be equal to the water flow. So pretend the water is not flowing. Okay, the water is not flowing. You just swim across, and that's all the effort. All your effort goes toward crossing the river. And now water is washing you downstream. So you also need to fight this velocity. If you want to go against directly, you'll have to fight water by heading the speed to the left, velocity to the left. So your overall needs to be this much velocity. So to be completely canceling the flow, this is the flow of the water, you need your x component to be equal to that, equal and opposite to the flow. It's like whatever the water is flowing, you swim across against it. So this is the cosine theta. So it's 0.5 times cosine of theta has to equal to the flow of the water. So you can see it's very similar to what you said, but I would set it to this equal to the cosine theta. So the cosine theta would be 1 over 0.5 as 2. And can we get a cosine theta that's equal to 2? You can see that no such angle exists, right? The largest angle for cosine of something is 1. So you can see that in this case, you have your effort. You can think of your effort as part of the effort is crossing the river and part of the effort is fighting the water flow. But the biggest effort you can have is 0.5 meters per second. It's already smaller than the flow of the water. So the component of that effort, a component of that speed is going to be even smaller than this. So there's no way you will be able to go directly across. In this case, most likely you will be auto washed downstream by the water. So in this case, we would answer D. No such angle exists. So going back to the pre-lecture question that you have already done, see, this is a swimmer relative to the water with this much speed. And this is the water flow. You can see that it's similar to the question we answered that she will be able to cross the stream. Sure, but since this velocity is smaller than the flow of the water, she can never go directly across. She will be water downstream to some place downstream. That's on the right hand side of X. So it's this answer. Okay. Not upstream, but downstream. Now let's look at a question that involves 3 different objects. Previously, we been working on relative motion, we add up 2 quantities. Now it's up 3. So let's take a look at this. You're on a train. Okay, the train traveling relative to the Earth with 15.
Professor, your microphone's a little bit muffled.
Okay. How about right now?
Yeah, it's a lot better.
Okay. So relative to the train, 15 meters per second. You run west inside. So your velocity relative to the train is to the west 3.5, and then at the same time you throw a ball directly north relative to the train. So up. Five meters per second. What is the speed of the ball relative to the ground? Okay, so that is the question. Take about a minute or two, and then we will come back for a discussion. Maybe a minute or two on this question.
Professor, I'm sorry. We throw it north or do we throw it up?
North. So
Oh,
this is on a flat view, north. Hard to
Alright.
draw up, yes. So for people who come back, I wrote ball is thrown relative to the train, but no, it's you throw the ball relative to yourself. Okay, so the third velocity ball is relative to yourself with 5 meters per second. So another 15 seconds to finish voting. Okay, let's take a look at this together. I have to go ahead and close the poll. And this is our results. Okay. All right, so we now have 3 objects, but it's okay. The math still follows. So ball relative to the ground, the beginning and the end, you can insert how many relative objects in there as you like. So let's see what are the information again. The ball is throwing relative to yourself because you are throwing the ball, right? Okay, plus you are moving relative to the train, and the train is moving relative to the ground. So I inserted 2 objects in there, you and the ground. So now let's add all of these constant quantities together. Ball relative to you is throwing in the y direction is 5 meters per second in the y direction. Okay, so these are vectors. I need to put vector sign in it. U relative to the train is 3, and that's to the left. So left x hat, right? Negative x. Train to the ground is 15. Moving to the right-hand side, that's positive according to my definition. So this is going to be 11.5 x hat plus 5 y hat. Okay, so 11.5 x hat and 5 y hat. So overall, the speed of the ball is going to be 11.5 squared plus 5 squared and square root of that. That's the speed of the ball. And that's 12.5 meters per second. Okay, so these 2 different directions, but the vector addition still adds up to be true. So yes, C is correct answer. Okay, so you can see in relative motion, you mostly need to make sure you follow this vector addition equation. You have 3 objects, insert 1 more in between. Okay, so I want to touch upon circular motion, and we'll finish our discussion next time. Now, this one I'm not going to vote, but simply just going to ask your input right here. If you have a car driving around with a constant speed in a circle, do you think there is an acceleration on the car? Do you think there is or no? If there is no, because the speed is constant, there's no acceleration. Do you think that would be correct? Anybody? So if the car driving was constant speed, circular in a circular motion, right, thank you. Yes, someone said because the direction is changing. Even though the speed is not changing, the acceleration is the change of velocity over time. Velocity is a vector, right? Vector has directions. So to change the direction of velocity, as you can see, the velocity of the car as the tangential direction is changing all the time. You need an acceleration, yes. So this is the acceleration we're going to look at for circular motion. in which direction the velocity is changing. You can see the velocity at two different instants. This is the first instant, tangential direction, and next time is in this tangential direction. So the change is described by dv, right? So dv, you can see that because v and the change of v are so close, you can view these two are the same magnitude, and you're looking at, so this is a little bit of math. Looking at a circle, I would argue this arc length is r d theta. And why? How do I know that? Because if you go all the way around for 2 pi, the circumference is 2 pi r. So if I only go for a certain little angle, a very small angle, what is the circumference relative to, what is the arc length relative to the angle? So S is r d theta. So by doing that, you can see this is, when they are so close together, this is kind of like the arc length, and dv, the arc length, is v, this is the radius times angle d theta. So dv is v d theta. Now dv over d theta happens to be acceleration. Sorry, no. dv over dt happens to be acceleration. So acceleration dv over dt, and dv is v d theta. So v d theta over dt is your acceleration. So the acceleration needed to maintain a circular motion is v d theta over dt. And we will continue to talk about how do we continue to work with d theta dt in the next class. And we call that omega, which is the angular velocity. But we will save that for the next class, okay? All right. Okay, so that's all for today. I will, yes, Fabian, it is, the direction will be toward the center of the circle as it turned out. I'll see you guys next week.
Thank you.
Thank you,
Thank
Professor. Have a
you.
good one.
Professor.
Thank you, Professor.
Thank you, Professor. Have a good week.
Bye, you too. Have a good week.